ladies and gentlemen, if we go to baseline and we scroll down, we'll see count clinics is 0. Let's go to baseline with 10 clinics. Okay, now we'll see 10 clinics there. So here we see these different experiments have different assumptions about the number of clinics. So let's, having run the baseline, let's go run it with 10 clinics. Okay, here we go. Okay, so let me rehearse that again. You right click on this baseline with 10 clinics and say run, and we're run. So we have, you'll notice that there are these clinics around here, and the clinics are spread in many regions of the model, but are particularly distributed out here with higher income populations to the right. Ladies and gentlemen, let's scroll down here to the level of a clinic, okay? We're going to scroll through these clinics. Here's a clinic here, for example, the first clinic, second clinic, third clinic. And you'll see that most of the clinics are under serving. But this one, for example, has served somewhere like 452,000 people, although of those 375 have balked. So this is a clinic that involves a depiction. This is a hybrid model where we have a stage series. When a person comes into the clinic, they undergo treatment once they've secured the attention of a healthcare worker, once they've been allocated this healthcare worker, and then, ladies and gentlemen, there's a set of processes by which they're triaged and determined, okay, do they need counseling? If so, they're assigned a counselor, which might change their behavior. Otherwise, they're just released to the population. Individuals who wait too long a period of time are able to balk here and can depart without being seen. Let's go see how that's captured. If you double click on clinic here, okay, one thing you'll see if you go to assign healthcare worker, here we could see down in the advanced area, I think it is, excuse me, it's in the, yes, it's in the advanced area. There's an area called timeout, where basically after a certain number of minutes, a person may balk, may leave the clinic, okay? If they're not seen within an amount of time. And what's that amount of time prescribed by? It's drawn from a triangular distribution with a mode of 20, a max of 45, and a minimum of 10, okay? So for each person, when they come in, we determine their timeout, and if they stay longer than that number of minutes, they can leave by balking. In other words, leave without being seen, okay? And that's this path to departure that occurs there. Now, sorry? What advanced?
There's advanced below that as well, see? Connected blocks.
Okay, so...
Scroll down too far and miss the first
Oh, yeah, this one here, I think, is... really, it should be called Advanced Java, and the one above should be called just Advanced or Advanced Process. So this is normally used to set sort of certain features that are more Java related, like is it a person flowing through here, or is it some models have animals. There's a veterinary hospital, there'll be a dog, or there'll be or maybe it's a different sort of person. So there's maybe homeless people and non-homeless, and they might be different agents. The point is that this allows you to set additional features. I think it's confusing they called it advanced as well. Now, in this model, these models, discrete event models, are specifically used to capture situations where we have resource-limited processing flow through a set of flow through a workflow, and the progression of an individual along this workflow is mediated by availability of resources. So in this case, There's nurses and counseling resources available. And in order for someone to get treated, they need to be allocated a nurse. They need to reserve a nurse. Once being allocated, they can undergo treatment. And then if they are assigned to counseling, they need a counselor in order to undergo counseling. So these resources are kept track of by any logic as part of it. And if there's too few nurses, there'll tend to be a large queue waiting here, and people will often leave without being seen. Okay, so this is what's called the discrete event model. This characterizes the flow through a workflow, which is resource dependent. And this resource dependency determines how long people wait, the waiting time, the size of the wait list, and will often determine whether or not, in fact, they complete the process as planned or whether they bulk and go back into the population while remaining infectious. So this is one feature of the model. An additional feature of the model that is worth emphasizing if we run this is, and I'm just going to run it on the baseline. If this, we will notice that there's quite a bit of activity here. You notice I'm keeping track of, for different population groups, low SES groups, as well as high SES groups, the distribution of counts of infections they've had. This is an infection by which they can recover, and it's treatment-mediated recovery, in fact, in most cases, or in many cases. And what that allows to happen is that a person could get infected many times here. And ladies and gentlemen, this histogram up here depicts the number of times they've been infected for people of high SES and low SES. And there's one big distinction. You'll notice that for those who are infected, the curves are fairly similar. The high SES has a longer tail. But then a large fraction of high SES are never infected at all. And here's another curve on the left-hand side, which depicts for each individual, an individual being a dot here, they're placed here according to their income on the x-axis. So this person here has an income of about 5,000. And according to the y-axis, on the count of times that they've been infected. So that person with a income about 5,000 has had a number of times infected over the course of the model of about 30 or so, plus or minus. Now you'll notice a trend here. Does anyone want to broadly characterize this trend?
Step change.
So there's a bit of a step change. There's a bit of almost a tipping point where if people have a high enough income, what happens? They don't get infected at all. And broadly, there's some, although somewhat perhaps nonlinear sort of pattern here between income on the one hand and infection count on the other, where for very low incomes, it's fairly stable, but as the income increases, there's this decrease and then it kind of drops off. To these higher income individuals, there's very few people infected. That is an emergent pattern coming out of this model. We didn't program that into them. We didn't program this in, we didn't program that in. These things are emergent patterns. They're coming out of the model. This is kind of the prevalence among high SES and low SES. And what does that reflect, do you think? If I told you, and this is true, that the x-axis here represents income, and the y-axis is random, and people are connected if they lie within a certain distance of each other, what would you generally say about mediating factors that might determine this disparity? There's many factors that determine whether an individual gets infected here, right? Their current infection status, their connection with others, their placement. But why is it that individuals who are higher income might have lower burden of infection? Well, lower income individuals are down here, and those individuals are what? They're in a more crowded environment, right? They tend to have more people around them that are in close proximity, and therefore their connectivity is higher. So that contributes here. In general, the actual prevalence levels are a complex combination of aspects of the natural history of infection and their their particular social networks, etc. Let's go, though, see how this curve changes for other scenarios. So, ladies and gentlemen, I'd like to go run another scenario. Let's run this one baseline with 10 clinics, okay? Now, these clinics are spread throughout the population, and many of them are actually way over here in high-income areas. But let's go see them in throughout the model. So I'm going to run this thing flat out here, and it's going to run until it completes, and then we'll see this same graph here. Okay. So we're running it out. Once again, we have some depiction here. Okay. So now this is with this counterfactual where we have 10 clinics in place. How has this curve changed? Well, it's changed in some interesting ways. Right? So one thing is we still do have, at a broad level, high-income individuals being less vulnerable to infection, and low incomes being more vulnerable. But we also see quite some differences in where the infection is circulating. And there's this curious nonlinearity here associated with an income of about 2,000, where above that it's suddenly higher, and then it sweeps down, and then goes sort of largely much less infection at this level. You'll also notice that this is a rather steep gradient compared with the more gentle gradient before. But it's an example of how those emergent patterns can change quite dramatically with different situations. Let's try running the model with 3 clinics. So I'm baseline with 3 clinics here. Okay, and I just ran that, and I don't see anything happening. Nothing at all. What's going on? Let's try that again. Nothing at all. Well, ladies and gentlemen, for this I want to introduce you to another feature of any logic. If we go to this baseline with 3 clinics, what happened is that the infection by happenstance died out. But you'll notice it happens every time we run that model. And it's a reflection of stochastics. It's a reflection of the fact that certain features in the model are uncertain. Okay, and I'll show you that in just a minute. But if you were to scroll down in this baseline, and you were to go down to the randomness thing, you'll notice that this experiment is set to run with what's called a fixed seed here. And what that means is that this particular thing is set up so it's completely reproducible. If you run the experiment again, you'll get exactly the same results. Let us instead set it to random seed. Okay? What this will mean is that each time we run it, we will get a different particular set of circumstances with respect to chance, happenstance. Okay? I'll go into that more in just a minute. But let's go there, baseline with 3 clinics, having changed it to random seed, and let's run it again. Okay? Here we go. And now the infection is actually taking off, and we'll run it out to its conclusion here. You'll notice that there's fewer clinics here, but there's one of them in this kind of lower income area. And else we'll see this kind of pattern again. We have a gradient here. It's not quite as stiff as to when it dies out, but for the lower income individuals, we're tending to have somewhat below the higher. Okay.
Won't we all get different results?
Sorry?
Won't we all get different results with the random?
Yes, and let's run it again. Let's run it again. Okay. So we already saw one effect of that randomness, that sometimes it didn't take at all. But let's run it again, and we will see how the differences lie. So here we can see the number of infections borne by that population over time. And Here we go. And now we'll see slightly different results indeed. So the shape of this is a little bit different. Well, it's quite a bit different from the one I just ran. It's a bit different from the baseline. We'll try that again. And that's a reflection, and this time it just died out altogether. Died out again this time. Died out again. So there's something about these clinics that is leading to it to sometimes not persisting within the population. Let's run it out again. Okay, and this time we'll look to see what this looks like. Okay, and now we see this sort of situation where it's once again we have this kind of sudden change. So this graph here is an emergent reflection of the model. The particulars of its shape depend on a number of factors. And amongst other things, they depend on the exact placement of clinics, where the clinics happen to be relative to the lower income, middle income, and kind of higher income areas will tend to put its footprint on this graph. Because if a clinic is nearby, many people will get treated, and therefore they may be in a situation where they have lower burden of infection. If there's a region that they have a less dense network, but there's no clinic present, those individuals may be at a somewhat higher exposure levels. High income areas tend to have very low density of the network. So here we see that this emergent pattern depends some on the particularities of the situation. Some of its broad features are fairly regular. It has these regularities across different runs of the model, but it certainly differs in some of its particulars. Now this brings up a couple points. First of all, these exhibit stochastics, exhibit randomness. To develop confidence in them, we often will need to run the model many times so that we are confident what we're seeing is not simply a fluke of one run, but the result of a regularity in the model. There will be variations in the results, but also some of the stochastics, or excuse me, some of the emergent patterns that we see are patterns that shift a lot by different assumptions about the model, different intervention regimes. And as I think you'll appreciate, if we were depending on a particular association in a statistical sense between income on the one hand and infection count on the other, the details of that association will be modified by our intervention regime. If we put in place one set of interventions, we may see a somewhat different relationship here than another. And so in these models, we may, for example, wish, and I'll be breaking for lunch here in just a moment, we may wish to have, for example, interventions that focus on low SES people. So down here there's a scenario which says focus on low SES, 95% contact rate among low SES individuals, for example. Here, ladies and gentlemen, we're going to have a lower contact, and we do, in fact, 5 clinics in place as well. And you know, we could test the outcomes on this. In this case, we focus specifically on low SES individuals, and we're going to examine how does that change our profile here. But to develop real confidence on this, we'd need to run the model many times. And AnyLogic provides what's called a Monte Carlo export for Monte Carlo experiments, which allow us to do that very readily. So they can run the model, say 100 times over, accumulate the results, and summarize them across those realizations. In this case, our focus on low SES individuals has tended to lower somewhat the burden of infection among them. But as you can see, there's still a persistence of infection both in them and in a the higher income population. We could look at 75% contact rate and find then its association. So one of the features that we have to be cognizant of when it comes to counterfactual situations, when it comes to simulating intervention regimes, is the fact that we have a context where the data generating process that applies is different. In other words, when we're depending on statistical analyses, one of the cautions is we're depending on data from a particular context, and almost invariably it's a context in the past. And to the degree that we actually modify the data generating process, the causal pathways that gave rise to the data, we can expect to see changes in our associations that we pick up and that we study with statistical data. As a result, when it comes to anticipating, projecting forward into counterfactual regimes, statistical data has to be treated very carefully, because we may be projecting forward into a new data generating regime where there's no data yet in place that allows us to really be firmly understanding the associations. With dynamic models, while they'll incorporate as a key component statistical understanding at the micro level, at the level of particular causal pathways, they can help us reason about the implications of particular counterfactual regimes, where these associations that are depended on by statistical models may be rather different in their particulars. These counterfactual uses of models are perhaps the foremost uses for which dynamic models are sought, and can be quite detailed. This agent-based modeling that we've been looking at is particularly notable by allowing us to formulate very specific intervention regimes that, for example, can be targeted based on a person's history, based on their network position, based on their spatial position, based on their particular characteristics in terms of heterogeneity, their particular demographic groups, etc. And as such, agent-based models can be very fruitful tools for examining specific types of interventions. This particular model that we're looking at here considers many types of interventions, from behavioral counseling to changes in the number of clinics, to changes in contact rates, and to changes that affect the duration of infection. And all of those can be comfortably examined within the context of an agent-based model by changes to parameter values, or by changing things such as the network, the assumptions involving network interaction as they are captured at an individual level. So agent-based models can be quite fruitful tools for examining counterfactual intervention regimes. Those intervention regimes will yield emergent behavior that's often quite different from what we see for the baseline case. And within these models, we can often use the expectations for an intervention that are developed by model exploration to formulate intervention strategies, which then can be tried and compared with model anticipation. The idea being that one of the best ways to test a model like this is to actually try examining a counterfactual situation through an actual intervention, and to use it to cross-check what the model anticipated, to improve the model design, improve the model characterization of the external situation. Sometimes putting in place interventions allows us some of the best opportunities for learning to improve the models. Okay, so that's all we have time for this morning. I had planned going into a cost effectiveness model, but we're going to have to leave that for a later session, one where you can look at the CE plane and assess activity-based costing information. After this lunch, we're going to dive in and build our first model, okay? And that model is going to allow us to capture a heterogeneous population of individuals, and eventually we're going to put in place some comorbid representation of comorbid conditions before the afternoon is out, so that you'll come out of here with an understanding of how to build state charts that capture a fairly articulated depiction of a person's health state and risk factors. Okay? So that's all for now. It's time for lunch. And Jeff, what time are we back from lunch?
1:30.
1:30. Okay, thank you very much. And I've already posted several of the videos, and I'll post the one from this session. Question? Was there a question there? Yeah.
So with the examples of, based on the 3 clinics, are you randomly just sort of selecting location?
Yeah. So if you like, I can show you where that's done. We're going to be going into this, how you actually build these models quite a lot. But if we go here and we go into Maine, okay, within Maine, we're going to go to, there's an area called clinics, okay? This is a population of clinics, just like this population of clinics. And if we go and we go down to this initial location, what we'll see here is that we're setting the location of the clinic to be a Y location that's random, and then we can set the X location either according to how the population is distributed or according to a uniform distribution. Okay, so we can have clinics placed more in where the population tends to be, or we can have them placed according to a uniform distribution. And I think the examples we were running, they were being placed according to a uniform distribution, but we could examine the effects of changing that so they're placed where the population is. Okay, great question. Any other questions? Yes?
Is it the same thing that the links between or the contacts between individuals are also formed?
So great question. So the contacts between individuals here are set. If we go to, actually it's the population. If we go to the population, we'll see, and we scroll down. Excuse me. It's actually in Maine itself. We scroll down in the population. There's a space and networks area here in Maine, and that dictates what assumptions to have about the populations within it. And you'll notice that we say that this is a distance-based network where people are connected with a certain distance threshold. So if they lie within a certain, if a pair of people lie within a certain distance of each other, then they'll be viewed as having a connection, otherwise not. And by changing this distance threshold in different interventions, for example, we could change the assumptions, this distance threshold here, we could change the assumptions about how thickly people are connected. Here, because people are being distributed according to income in a more, in a way that's drawing from a non-uniform distribution. I draw from a random income from a custom distribution. Let's draw random income. They tend to be clustered. There's more crowding on the left. There's more lower income people. And those lower income people are therefore have greater numbers of connections because they're connected to more people. And if anyone were interested here, there's this draw random income is just drawing from a log normal distribution. Okay, so we could. I thought it was a custom distribution, but we can impose an empirical distribution if we wanted to. Here it's from a log normal distribution with certain parameters. Is that helpful? Okay. Any other questions? Okay. Let's have some lunch, and we'll be back here at 1:30. Okay. Thank you very much.